Hello and welcome to a demo of the QustomWeld application. This is developed by CustomApps. If you have questions over it, you can go to customapps.com. Custom is spelled with a Q, by the way. All right, so the plugin is a plugin built inside of Abaqus CAE. So we'll bring up the plugin here. And for demonstration purposes, what I've done is I've started with a model that's about 90% of the way built, just to make things a little bit easier for us. If we look at the plugin on the top here, we'll have some icons like the user's manual. We have some workshop setups. We have some example problems that you can build and then you can run to see the results. We have licensing information, and then we have color coding and highlighting. All right. So in a model, we typically start by using this plugin. What we'll first start doing is building a model within Abaqus CAE. So whether we import the model from SolidWorks or CATIA, or we build it inside of CAE, it doesn't really matter. We can even import orphan mesh models from another third-party company. So as long as we get the models, we put it into the assembly and it's ready to go, then we'll open up QustomWeld. We'll assign a few defaults, and then we basically have 5 or 6 steps to do. We define the materials, the base material. We define deposition and beam welds, and then we define the robots, which control how the beads are laid down, and then finally the scenarios, which controls the order in which the beads are laid down. All right, so we'll start off with the materials. So essentially this is just a table of additional properties that the QustomWeld tool needs in order to do the welding analysis. So the steel is a material that's already been built into Abaqus CAE, and it maybe have the thermal expansion, the plastic properties, elastic, and so on and so on. So it has everything in there, but we still need a couple more properties in order to do the welding analysis. So one is the melt temperature, and that's the temperature at which the bead is inserted when we run the stress model. So when it's inserted, it's going to be inserted at melt temperature. And the other property is a cutoff temperature, which is just means that after 1200 degrees in this case, that any temperatures above 1200 will not cause any additional thermal strains. So we cut off the thermal strains at this given temperature. So essentially we'll create this table for all the different materials that we're going to use, and once we've done that, then we go define the base material, which is define the regions that are not welds. All of the base material that is not a deposition weld. So to do that, we can do it 3 different ways. We can pick on the cells, or in the case of 2D, we pick on faces. The QustomWeld handles 2D and 3D welding simulations. Or we can pick on all of the elements of the model, or we can just select a list of sets, which can either be geometry-based sets or element-based sets. So we pick one of those, and once we do that, we get a green check, and then we choose whether to assign all of that base region to a given material. Or let's say that, for example, you have a base material that has lots of different regions that have different material properties. Then you wouldn't want to do this. You'd define all those section definitions outside of QustomWeld. All right, and then the other thing you could do is right from the get-go, you can assign the element types for the heat transfer and the stress model. Okay. Then the next step would be the deposition welds. So you'll notice in the first 2 steps we have green check marks, meaning those steps have been completed. Now the deposition weld, we've created 7 or 8 welds here, but we still don't have a green check mark. And what that tells us is that there are still some elements that have not been assigned to either the base material or a weld. So until all of the elements have been assigned to welds and base, we're not going to have that green check mark. So let's just turn on the highlighting, and what we'll see is we have all these different colors for the welds, and these are beam welds and these are deposition welds. But then we have this cyan color, and this cyan color represents elements that have not been assigned to either. So we're going to create this deposition weld here. So I'm going to call it right bottom. and I just have a single material available. And under here we have film conditions and radiation conditions. So I'm going to use the default, which we defined when I initialized the model. But as the beads are being laid down, the surface of the bead is evolving over time, and what we want to do is put a film condition on it that evolves over time with it. So by selecting these, we can put the film and the radiation conditions to evolve over time. Okay. So you'll notice in the tree, the one thing that happened was this right bottom weld got created, and it has, when we open it up, it has this beads repository, and there's nothing in there. All right, so it automatically pops up the bead creation dialog. So what we have here, we see what we need to define. Basically 4 things. I need to create the geometry of the bead, or the elements of the bead, and then the directions of the path. So we're going to have a bunch of nodes that define the path of the torch, and we're going to define where it starts. And finally, we'll define the normals. Now, the normals are done automatically, but there's a few options if we want to change them. But we'll kind of see that as we go. So here's the first option. We'll do, the first item is cell picking, so it's a geometry based. So we pick the geometry. The next item is element edge picking. Now I have an edge here, so if I wanted to, I could just as easily pick the edge. But a lot of cases we don't have the edge. In fact, most cases we don't have the edge. So the default is this element edge picking. So I'll pick the edge, and let me just highlight these, and then we'll see by picking the edge, the plugin picks all of these nodes along the line of the edges. And then we're going to pick the start point. So we would pick either this point or this point as the start point. So I'll just pick it as a vertex since we actually have a vertex there. All right, so you notice all 4 of these are checked, even the normals, even though we haven't done anything. The default is by centroid, which means if we look at this edge and we draw a normal to point toward the centroid of the cross section, and then that'll be the torch direction. So 98% of the time that is fine. All right, so we'll use that as a default. Then it fills in all of these things, all of the normals. So if we wanted to, we could actually modify the normals themselves, or read from a file somewhere and populate that and customize it. But normally this is going to be just fine. Now the other thing I want to do, since we're defining this bead first, and this bead is actually floating in midair, so when I'm done, I want to reverse the order. So what I want to do is, just to make it easier to pick, I want to remove the beads as I'm defining them. And in the end, I'll just reverse them, and it'll make it easier to define the beads. Okay. So now we have one bead here. You'll notice that bead's been removed, so I'm going to stick to all geometry at this point, since we have it all. All right. So again, we've got everything defined. Okay. And finally, the last one. All right. So you'll notice when I hit continue there, it built the last bead, but then it just closed the dialog. The reason is after it creates a bead, it checks all the elements to make sure and determine if any of them still have not been assigned. And if they've all been assigned, then it automatically closes that dialog and doesn't reopen it. So at this point, you see the green check mark. It says, okay, we've got all the elements assigned to either the base or the bead materials. Now what I'm going to do is redisplay all of these, and now you'll notice we've got the 4 beads, and I'm going to highlight them. Now highlight gives you a warning. Sometimes this will interfere with double clicking, so it just gives you a warning. So if I look at the order, this is bead 1 and it's sitting in midair. This is bead 4, which really should be the first one. Now these two might be interchangeable, but certainly these two have to be reversed. So what we'll do is reverse order. All right, and then we see a more logical order. Now we really didn't have to do this because when we get to the welding scenarios, that's when we actually control the order of the placement. But it just makes it a little bit easier if we have roughly in the same order. So again, I'll turn off the highlighting. I just use it when I need it. All right, so now we've got the first 4 steps done. Now we've got to define robots. Now robots control how the beads are going to be laid down. They control the amount of energy put in, the size of the melt pool, the size, and the size of how large the flux is that gets applied to the bead as it's being laid down. So it has a bunch of controls on there. So for this model, we've got a robot defined for the left, for the middle, and then we've got a separate robot for the beams, which is the beam welds, which is a line up above on the top here, and then this white line here. And then we don't have a robot for here. So what I'm going to do is, actually I'll just copy this robot. And then we'll open it up and we'll see it has this welds repository, or we've got to assign the welds. But first let's see what the actual robot, what the parameters are. So when we look at a robot, this is a deposition robot. So we're going to have default robot movement controls, which is the torch speed and the dwell time. Dwell time is, when it first starts to put down a bead, it's going to heat up that base material for a short amount of time before it starts actually depositing material. And then we have torch controls, which is the amount of energy being put into the bead and the shape of the distributed flux that's being applied. Essentially, this is the shape of the melt pool. And then computational controls, whether we're going to do a Goldak double ellipsoid or a constant flux, or whether we're going to put the bead down in continuously, element by element, or by big chunks of elements. All right. And if we do big chunks, we can do the number of chunks, we can specify how many chunks, and the scale factor is just a way when we pulse the energy onto the bead, how quickly we pulse that energy on. And we'll see that later, see a demonstration of that. All right, so these are all the parameters, and these are just defaults. So we see default, default, default. So when we assign the welds to the individual robots, they'll inherit these defaults, but then we can override all of them. All right, so we've got 4 different robots and 10 different welds. So it's probably most efficient to use this weld assignments tool to assign the welds to the robots. All right. So what we have here is the welds that are unassigned. So in the case of deposition welds, these have not been assigned to a robot. And over here we have, for a given robot, we have a list of the welds that have been assigned to it. So right now they're all empty. If we want, we can highlight the welds. So I do left 2. Oops. So there's the 2 left welds, and we've got the robot left. So I'll assign those, and then I'll do the mid welds. I'll assign those. Oops. I forgot to move the robot, so let's move those back. All right. And then if we want, we can highlight the ones that have been assigned. So based on where our cursor is. All right, and then robot right. So those are all the deposition welds, and then we'll assign. There's only one beam type of robot, so both of those will go there. All right, so now we look, there's no more welds that have not been assigned, so we hit OK, and what that does is it assigns the welds to all of the different robots. So the robot right, we'll just double click here and we see all the parameters. Basically, these are all those defaults that we had seen when we defined the robot. So they're all the same for all the different weld beads, right? So if we want to change any of them, we can change any of these colors that are in cyan or white. All right. Some of these columns are just for informational purposes, like path length, for example. It's just to give you an idea how long the path is. Energy ratio, that's a very useful number. It just tells us how much input energy divided by the actual energy to melt the particular bead. So usually in deposition welds, we're talking somewhere around 10. So this is not a very realistic model. So usually it's between 5 and 10. Then we have things like, since this is all continuously laid down, the chunks doesn't matter. But then we also have the chunk length versus torch length. So we have some informational stuff in there. Now, if you had, let's say, you're doing this on a laptop and you don't have the resolution, or it's just too big for you, we can display only the ones that we're interested in, so it'll make it a little bit easier in some cases. All right. So the robots, like I was saying earlier, the robots, they determine like the energy and the shape of the distributed flux, but they don't really determine how they're being laid down. So that's what gets assigned in the welding scenario. So right now we've got a green check on the robots, which means every single weld has been assigned to a robot. So the next step will be to go ahead and create a welding scenario. So when we do that, we give it a name, and then we just say the default cooldown time between beads. So when a robot's putting one bead down, before it goes to the next one, it's going to let that one cool down for a certain amount of time. And this is just a default, and we can override it. So once it's generated the defaults, now it can generate all the different robot controls. So we'll just, again, focus on the robot right. All right, so this dialog really controls the weld placement from this particular robot. So it controls the sequence of the welds. So by default, we say we're going to do it sequentially, meaning we're going to put the right bottom weld down first, and bead 1, 2, 3, and 4, and then go to the next one. Now there is an option to do simultaneously. Now this really doesn't make physical sense, but in many cases it might make sense numerically. For example, you have a bunch of spot welds. You want to do them all in one single step. Maybe you put them all simultaneously, and then the next step you do all the deposition welds like we have here. But even when we do simultaneous, the beads themselves are sequential. You notice the start time for the bead starts at 0, and then this is the amount of time it takes to actually weld it, and then it cools down for 300 seconds, so the total time of 325, and then it starts the next bead. So these columns give us a quick indication of the times for welding. And then if we wanted, let's say we actually want to do the top weld first, we can move it up. And remember, when we were looking at this, we said this weld and this weld, or this bead and this bead, we might want to reverse. So if we want to reverse those two, we could. And then, so again, like when you see gray, of course, this is stuff you can't actually go in there and modify by hand. So you'll see you can change the cool down time between the beads. You can change the direction. Let me show you what that looks like. So let's say we're at right bottom, bead 4. We want to reverse it. You'll notice you see this yellow. It's just a yellow arrow. And if we reverse it the other way. So it gives us an indication of the direction of the weld. All right. So we can control the torch directions. And then, let's say we have a weld with 30 or 40 beads. It may be that you want to do some scenarios where you don't do the last beads. You want to see the effect on things. So you can turn off the individual beads. All right. And then there's one last option here, which is expanded, and that's essentially exactly the same as sequential as far as time. The only difference is that when it puts down a weld bead, instead of putting it down in one Abaqus step, it puts it down in two. It puts it down in one step where it's placing it, and then another step where it does the cool down. Now the advantage to that is you can set different time incrementation controls for the heat up and the cool down, so you can do the analysis more efficiently. So in this case we'll use expanded. The other robots by default use sequential. So we'll kind of see how that plays out. So assuming that we had gone through and made the modifications for these different robots, then we would go into this summary and just kind of take a look at it. So we have sequential. We have 3 robots that are being laid down sequentially. Now if you look at the step number, what this says is they're all being laid down in the same step. Now whether we want to do that or not is up to us. But the one thing that QustomWeld will require is that if the placement is expanded, that has to be in its own step. Because what it'll do is, like I said, it breaks down the heat up and cool down into its own steps with its own controls, time incrementation controls. So that has to be done independently from other welds. So it's only, if you're doing expanded, you can only do one weld bead per step. So if we wanted to, though, we can just say, let's just do all of these in separate steps, and we could just break them out. All right. So that means this robot would do its weld sequentially, followed by this one and this one. So we'll just extend the time. All right. So once we've decided on how we want to do that, we said, okay, that's fine. Now we'll see a green check mark there. And the last check mark is this analysis step, which is just setting the convergence controls and output controls for the analysis. So we had the first 3 steps, which were not expanded. So here's the controls. We have maximum allowable time increment for the heat transfer and maximum allowable temperature change for the heat transfer. And then we have output controls for the heat transfer. And then with stress, we just have maximum allowable time increment and output controls. Now the expanded steps are a little bit more interesting because we have separate controls for heat up and cool down. So here's heat up time increment, the heat transfer. We have the heat up max time increment, and we have the cool down max time increment. And then the allowable temperature change, we have the allowable temperature change in the heat up of the bead, or the placement of the bead, and then the cool down of the bead. So again, we can change those to speed things up. And then we have the usual output type. One thing that's interesting about the expanded step is we can terminate not just by the time, but by temperature. So if we put down a bead, we can wait for that bead to cool down to, let's say, 300 degrees before we go to the next bead. So that can save time. So instead of putting 10 minutes of runtime, it might terminate at 3 minutes or 5 minutes of runtime. So it really can speed things up. And then again, with stress, we have a different maximum allowable time increment for the heat up and the cool down. All right. So when we hit OK, now the plugin is doing the final step. It's got everything that it needs for the analysis. Now it puts it all together and builds all the things in Abaqus CAE that it needs. Now it uses a bunch of table collections because it uses user subroutines to calculate the Goldak flux as it's moving. So it builds a bunch of table collections and things that are used for the user subroutines. All right, so essentially we've got a run-ready model where we can just go ahead and run these and we're ready and we're good to go. All right, so what I want to do now is open up a previously built model. It's a little bit different than what we have been building, but it'll show all the concepts. All right. So what I'm going to do is do an animation on temperature. And let's actually go one increment at a time. So if you look at this, we have basically three different types here. We have a continuous Goldak. So this is a Goldak flux being applied continuously. This is the heat transfer, so the material is being laid down as it's gone. Here we have a beam weld, which doesn't deposit material. It's just a moving torch. In this case, it's a conical shaped torch. So it has a top radius that's typically larger than the bottom, and then it tapers down to a small radius at the bottom. Then we also have something that's similar to a Goldak torch, except we're putting the entire chunk down at one time. So if you look at how we're doing that, again, this gray color is the melt temperature. So the single chunk, so right there, the single chunk has melted the entire bead, but it did so in the time, roughly the time that it took for this torch to traverse the length of the torch, really. So it does it over, kind of pulses that energy over a short period of time, and then the rest of the time it just cools down before it goes to the next bead. So this is what we mean by chunking. So sometimes this is very useful if you have a model like this in some ways that's an extruded model. You can do this chunking and it can get very good results. In most of the section of the bead. And then we have this beam weld. You'll see as we do the animation, this thing kind of oscillates just because this is such a coarse mesh. It really, the flux is applied over such a small region that it fluctuates quite a bit just based because of mesh density. So let's actually do the animation. We'll see that. See, so you see it kind of pulsating a little bit. This has a better mesh, so that pulsation is much smaller, not nearly as profound. And then over here we'll see chunking done not with one chunk, but with 4 chunks. So we see the same kind of thing. It's just heating up with the different number of chunks. All right. Then when we go to the next one, we'll see other beads being laid down. All right, so we see it moving along. And then we see one here in the back. So you can see we can have all kinds of different welds going at the same time by different robots. We can simulate all of that with this tool. All right, well, this has been kind of a quick demo of the QustomWeld tool. If you have questions, don't hesitate to call us. On our website, customapps.com, and custom spelled with a Q. There's information how to contact us, more information about the plugins and other offerings that we have. And again, thanks for your time. I appreciate it.